A cold winter's day under Stagfield at the University of Chicago, a group of the world's smartest physicists gather under the abandoned grandstands. The room is full of voices and speculation. The majority of the space is taken up by a mountain of graphite, 20 feet tall and 25 feet across. Lurking inside the structure is an almost microscopic amount of uranium by comparison. The time comes, and while the brightest minds gather around the control panel, the startup is initiated at 9:45 a.m. By 10:37, the room is anxious for results, and the wooden control rods laced in cadmium are ordered out of the pile. No result. This was due to an automatic response, sending all control rods back into the pile. At 11:25, the pile had cooled, and so had the physicists' heads. It's time for a lunch break. The world's first nuclear chain reaction would have to wait. Hello and welcome to Come Hell or Heavy Water, where we talk about nuclear history, bombs, accidents, and energy. Today we are going to talk about some of the first nuclear reactors, whether they were experimental or used for plutonium or energy production. I want to start off where it first began, the definition of the atom. In 1897, Joseph John Thomson discovered the first subatomic particle, the electron. This discovery led to a completely new definition of an atom. Now the theory at the time was that atoms were singular objects. This was proven wrong, but it was a good thing, because now the field of atomic science could, explode. Eventually, this will lead back to the United States, but in the meantime, we need to head over and take a tour of Europe, where scientists were now experimenting with these new neat particles called electrons. Germany, in 1905, one of our key players, Albert Einstein, developed the theory of relativity. In doing so, he showed that all matter was comprised of energy and that energy could be released in enormous quantities. While this was incredibly exciting, no one knew how to release it or to what extent this energy could be released. A trail of breadcrumbs started to be placed, though. Ernst Rutherford was experimenting with nitrogen particles at Cambridge University in 1917. He would bombard nitrogen atoms with ions just to sort of see what would happen, and boy howdy did something happen. Rutherford found that when an ion hit the nitrogen just right, it would create an oxygen particle, and a whole new particle, a proton. Atoms were very slowly starting to take shape as more parts were discovered, but the center remained a mystery. Up until, that is, another Cambridge physicist, John Chadwick, unlocked the mystery in 1932. He discovered that the center was composed of a neutral particle devoid of charge. This would lead to an astounding discovery that one could throw these at other atoms and watch them split. The neutron was the ideal subatomic particle to use due to its neutral charge. They could essentially butt into any atom and divide it. Now, people began to do this all across Europe, but in particular Italy and Germany. And this was on the eve of World War II, so that combination is a bit scary. Most physicists in Europe, however, were either Jewish or anti-fascists. This leads to another one of our key players, Enrico Fermi. While working in Rome in 1934, he was bombarding multiple elements with neutrons and discovering that this would lead not only to a release of energy, but the creation of a whole new element. He followed the periodic table, discovering new elements every time he launched a neutron. Eventually, he got up to uranium, and when the atom was hit, radiation was observed and energy was released, but no new element was to be found. While he and his team did not realize this at the time, they had just discovered nuclear fission. The hunt was on to find out what had happened to the uranium particle and why there was radiation floating around as a result of its bombardment. Furthermore, during his experiments, he had found that when the neutron cannon was on a wooden table, it would lead to better results. This was due to the wood moderating the neutron or slowing it down. While this was good to know for their experiments, it would be fundamental in the creation of a nuclear reaction. For his experiments, Fermi would be awarded the 1939 Nobel Prize in Physics. Now we get to how Fermi got to the United States. His wife was Jewish, and seeing the rise in anti-Semitic fascists across Europe, Fermi took the opportunity given to him. He told his children to pack for a short trip when they went to receive the award. While in Sweden, him and his family escaped to the United States. And this was a trend for a lot of physicists, scientists, and intellectuals. In fact, Albert Einstein was already in the US by the time Fermi had arrived. It's almost like fascism, the worst political system ever imagined, does not have a place for smart people. Who would have thought? Anyway, back to the atom. Our story now leads to Germany. Yes, Germany in 1938 was not the place anybody wanted to be. Two German scientists, Otto Hahn, a chemist, and Lisa Meitner, a physicist, had been working together for nearly 30 years. They continued Fermi's work until the summer of 38, when Meitner, being of Jewish descent, felt it necessary to flee to Denmark and eventually Sweden. Han had given her his mother's diamond ring in order to bribe the border guards with during her escape. After she made it to safety, Han continued their work, but now with the help of a research assistant, Fritz Strassmann. Miter continued to correspond with the two through letters. Han had identified barium as a result of neutron-bombarded uranium, but could not provide any explanation as to how it got there. Miter was now in Sweden for the 1939 New Year with her nephew, Otto Frisch. They met and began discussing Han's findings, as Frisch was a physicist as well. They were walking in a snowy forest when they finally sat down on a convenient log and started to do some calculations. They hypothesized that if barium was present after the reaction, and seemingly nothing else, that the atom had split into parts. Whether they knew it at the time or not, they were completely right. Miter had also found that 1/5 of the uranium's weight was not present. She speculated that it was released as energy, as Einstein's theory suggested. Now, at the time of this discovery, Frisch was working with another famous physicist, Niels Bohr, in Copenhagen. Upon his return, he told Bohr, who reportedly smacked his head and said, "Of course! Why haven't we seen this? Oh, what idiots we have all been! Oh, but this is wonderful!" Miter remained in Sweden for the war, and she was even offered a position on the Manhattan Project. She refused, believing that her discovery should be used for peace. Han remained in Germany for the entirety of the war and was offered a position as a professor in place of a Jewish professor, and he refused. He also refused to join the Nazi Party, and refused to join the Nazis' atomic program. In fact, in August 1945, when he heard news of the atomic bombings of Hiroshima and Nagasaki, he grieved that his work led to the result and briefly contemplated suicide. He received the 1944 Nobel Prize and continued to work in nuclear non-proliferation, being considered as a Peace Prize recipient more than once. Because of the times, take that as you will, Miter's contribution was overlooked and she was hardly recognized. However, Element 109 was named after her, and in my opinion, that will be remembered a lot longer than any Nobel Prize winner. Conveniently, Bohr was scheduled to leave for a series of conferences in the United States on the 7th of January. This was the 5th Washington Conference on Theoretical Physics, where Bohr made the first public announcement describing nuclear fission. As exciting as this was, it was also terrifying when the realization that this could be weaponized occurred. Very quickly, the immigrant scientists got together not only to warn the United States government that the Nazis were working on an atomic device, but also to inform them that they should be too. Einstein was recruited to help get this news to Roosevelt. A letter was written by Leo Szilard and signed by Einstein detailing the danger that they faced. It mentions the threat from Germany. Quote, "I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines which she has taken over. That she should have taken such early action might perhaps be understood on the ground that the son of the German Undersecretary of State, von Weizsäcker, is attached to the Kaiser Wilhelm Institute in Berlin, where some of the American work on uranium is now being repeated." Unquote. This letter not only jump-started the Manhattan Project, but for our interest, the continued development on uranium research. The continued research led several different scientists to eventually discover that when the atom splits, not only was energy released, but also a few more neutrons. Under the right conditions, if these neutrons hit another uranium atom, it would lead to further splitting, and thus the release of energy would continue, this time though in a chain reaction. This had some very important implications, mainly that a nuclear reaction could, in theory, be sustained, allowing the harnessing of said energy released. And thus, the idea of nuclear power became a reality. Kinda. The fact still remained that these experiments were incredibly small-scale, and arguably scaling them up was impossible at the time. By 1940, Fermi and Szilard had been experimenting with neutron moderators to slow down the reaction, thus making it more controllable. They found that the best moderator was carbon, specifically graphite. And with that, everything was now in place to begin assembling an experimental reactor. Pure graphite and uranium was purchased with the assistance of the government, and locations began to be cited. Different universities were looked at, but ultimately, the University of Chicago was chosen. At first, there was a concern about the experiment being so close to a large population center, but those fears were quickly put to rest by Fermi. He was asked what he would do if the reactor went haywire, replying, quote, "I will walk away, leisurely." Typical. Imagine if Anatoly Dyatlov, the plant manager at Chernobyl, replied with that when asked if the test should continue that night. Under the grandstands of the abandoned Stag Field was an empty racquetball court, which was large enough to fit the designed reactor. Construction began in February 1942 on top of a large pallet. Scientists, engineers, and workers stacked graphite blocks on one another, leaving a large gap in the center where uranium would eventually go. After 11 months of construction, 57 layers of graphite, 771,000 pounds of the stuff, 80,590 pounds of uranium oxide, and 12,400 pounds of uranium metal, the pile was ready for operation. Now it was time for a test. 48 pioneers of nuclear science gathered in this incredibly cold basement, as it were, and the experiment began at 9:45 a.m. with the assistant Walter Zinn remove the emergency control rod. Now it's important here to note that all of this was being done by hand. The danger here, in my opinion, was not fully recognized. I'm not a nuclear physicist and not claiming to be, but if I were asked to jumpstart a nuclear reaction by hand, I wouldn't. Another scientist, Norman Hilberry, stood by with an axe, ready to cut the scram line, which was a piece of rope, which would lead to the emergency control rod to fall back into the reactor, halting the reaction. Yes, you heard that right. The failsafe for the first nuclear reactor was an axe, a piece of rope, and a graphite rod. George Weil was mating the control rods on the floor and removed all but one, and at 10:37, Fermi ordered all but 13 feet of the last control rod to be removed. Before it even moved 6 inches, the emergency response was triggered. No, not the axe. And the automatic system took over and the control rods reinserted themselves, halting any chance of a reaction continuing. In typical Italian fashion, Fermi then ordered the crew to go to lunch. After returning from lunch at 2 p.m., all control rods were ordered to be removed and the reaction began. I'm going to take a quote here from physicist Herbert Anderson, who witnessed this. Quote, "At first you could hear the sound of the neutron counter, clickety-clack, clickety-clack. Then the clicks came more and more rapidly, and after a while they began to merge into a roar. The counter couldn't follow anymore. This was the moment to switch to the chart recorder. But when the switch was made, everybody watched in the sudden silence the mounting deflection of the recorder's pen. It was an awesome silence. Everybody realized the significance of that switch. We were in the high-intensity regime, and the counters were unable to cope with the situation anymore. Again and again, the scale of the recorder had to be changed to accommodate the neutron intensity, which was increasing more and more rapidly. Suddenly, Fermi raised his hand. 'The pile has gone critical,' he announced, and no one present had any doubt about it." Unquote. Measurements were taken and the output of the reactor was read at 0.5 watts, but they would later find the reactor was capable of reaching 200 watts in later experiments. After 28 minutes of operation, Fermi ordered the reactor to be shut down. Eugene Wigner, another scientist, had purchased a bottle of Chianti wine in anticipation for the event. They drank out of paper cups and signed the straw wrapper. Arthur Compton, who was working for the National Defense Research Committee, called a colleague, James B. Conant, and informed him of the success through code. He said, "The Italian navigator has landed in the New World." Conant: "How are the natives?" Compton: "Very friendly." I think this is very neat, as the code was not prearranged. Chicago Pile 1, as it became known, was the first of many nuclear reactors to be built in the United States. But our story does not end here. While some scientists, especially Hahn and Miner, abhorred the idea of using their research for nuclear weapons, the U.S. government and a select group of physicists were compelled by the idea. So during the whole process of discovering nuclear fission, they also discovered plutonium. While uranium is good for nuclear bombs, plutonium is ideal. Ultimately, Chicago Pile 1 was not just used to prove that nuclear energy could produce electricity, but more so was done as a proven concept of plutonium production. When the U.S. government saw that it had worked, and they wanted to ramp up production. The issue was that a reactor the size of Chicago Pile 1 would produce only minuscule amounts of plutonium. It was soon realized that a new mammoth-sized reactor would be needed, and a site had to be chosen. But this time, due to the size of the operation, it needed to be far away from a population center and have large amounts of cooling water at the ready. The site chosen was Hanford, Washington, near the Columbia River. The residents in the nearby town of White Bluffs, Richland, and Hanford were forced to move through eminent domain. Residents received very little compensation, even though a staggering $8 billion was allocated for this project. Something that's even grosser than that was the fact that 4 indigenous tribes still lived, hunted, fished, and farmed in the areas for centuries. They were kicked out without any financial compensation. The operation was run by the DuPont Corporation, so it wasn't like they were short on cash or anything. Construction encompassed an area of 580,000 acres, taking up about 50 miles of the Columbia River. The area housed 50,000 workers, but due to the secrecy of the project, none of them knew what they were building. The reactors were designed to be 120 feet wide by 150 feet long and 120 feet tall. That's about 12 stories tall. The foundation was an insane 23 feet of solid concrete with a quarter-inch steel plate welded onto every wall. This was to keep helium gas inside the reactor chamber. The core would house 75,000 machined granite blocks, which would eventually be built into a 36 by 36 by 28 foot cube housing 2,004 tubes, which the uranium fuel would be housed in. Fermi oversaw the first time fuel was loaded into the reactor on September 13, 1944. Okay, quick side note, that's my birthday. Also on my birthday, the process of overhauling the fuel in Chernobyl began, which was the prep for the ill-fated test. Maybe that's an omen that I was meant to study nuclear history. Anyway, Fermi only ordered 1,500 tubes to be loaded. It wouldn't be until the 26th when the reactor achieved criticality and began producing plutonium. It would later be named the Hanford B reactor. Plutonium produced here would be used in the Fat Man bomb that was dropped on Nagasaki. General Leslie Groves, the overseer of the Manhattan Project, is quoted while discussing the production. Quote, "It is a phenomenal achievement, an even greater venture into the unknown than the first voyage of Columbus." They, just like Columbus, probably didn't see how they were ultimately working against the greater good and world peace. After the war was over, 9 more reactors were constructed at Hanford. They were all used for plutonium production. Energy was just a byproduct. The B reactor was shut down in 1968, and all reactors on site were decommissioned by 1989. Now the Hanford site is used to house nuclear waste. And that's the story of the United States' first reactors. While the intention of some of the scientists working on the project was peace, ultimately the first reactors were used for war. I don't know what that necessarily says about my country, but I don't think it's anything good. While we had the luxury of the top nuclear scientists working with us, the other country I wanted to talk about, the USSR, had a much rockier start to their nuclear program. With the scientific capitals of Berlin, Copenhagen, Chicago, and Berkeley all working on the puzzle of nuclear fission, the USSR was not about to be left out. Leningrad in the 1920s was also a utopia for physicists, just as the other great cities in Europe were. Communism, well, Leninism, promised an electrified country, but very quickly Russia's geography bit her in the ass once again. Natural deposits of fossil fuels were few and far between, and the vast distances of the state made transport of both energy and fuel very difficult. Thus, a solution was needed, and the emerging field of atomic science was viewed as an alternative. But, just like here in the United States, the Soviets would inevitably use nuclear fission for bomb production, but we'll get there. In the meantime, there was a large group of incredibly bright and young people who were working off of limited knowledge other than the small bits coming in from the West. Imagine the zeal that was felt, a new promising state in the hands of the people. They were working for the future, for prosperity and equality. Ultimately, those ideals were hijacked, but that's way out of the scope of this podcast. One of these youths was the incredibly brilliant Igor Vasilievich Kurchatov. He was born in 1903, and in 1909 went to the Young Men's Public Gymnasium, incidentally, the school where Lenin graduated. He showed an excellent understanding of mathematics and had an incredibly sharp memory. His family moved to Smerovpol and enrolled him in the top gymnasium, where he graduated with flying colors. In 1920, he entered Crimea University to study physics, but going to university during the Russian Civil War was not exactly ideal. Only a dozen or so students were showing up to lectures, there were no textbooks, and no scholarships. Some students almost starved, receiving 400 grams of bread and only some watered-down broth. But none of that deterred Kurchatov in his studies. While a junior, he decided to transfer to Petrograd, and at the time, he dreamed of being a shipbuilder. This all changed when in 1923, one of his professors gave him the assignment of measuring alpha radiation in the snow. He fell in love with atomic science and began learning as much as he possibly could. He moved back to Crimea to make some cash, working at the hydrometeorology station, studying the tides. He then went to Baku to work in the Polytechnical Institute, and eventually back to Leningrad, where the Leningrad Physical Technical Institute called him to study with them. After the revolution, contacts with Western physicists were re-established, and the stream of information began to flow again. This led to a nuclear group being founded under Soviet physicist Abraham Ioffe, who was the one who re-established contact with the West. The group consisted give or take of a dozen physicists. Even though Ioffe was the head on paper, Kurchatov was the most knowledgeable and the unofficial head of the group. He was the one who secured funding for the group, 100,000 rubles, in 1932. In 1934, Kurchatov received his doctorate in solid-state physics. But he was also incredibly versed in nuclear physics as well. He was also the chairman of the All-Union Conference on Nuclear Physics in 1933 through 35. The second and third conferences were attended by physicists from all over the world. The group published more than 100 articles in the leading scientific journals in the Soviet Union and were creating experimental devices just like the ones in the United States. But we cannot forget to mention the environment which all of this was taking place in, the Soviet Union in the 1930s. For those of you who don't know, the USSR, Stalin specifically, was purging all levels of society in the 1930s. This became known as the Great Terror. No one was safe. Anybody could be called a counter-revolutionary or an enemy of the people. If you were unlucky enough to be put on one of Stalin's, Berier's, or Yezhov's lists, you would either end up in a gulag or against the wall. While frivolous executions were carried out, the purge was also social and cultural. Anything deemed anti-Bolshevik, anti-communist, or any other statist language you want to throw into the mix would be wiped clean and reshaped into the party's liking. Eventually, the NKVD made its way to the LFTI, claiming they had failed to meet the needs of industry, and went after its divorce from practice, whatever that means. From then on, discourse with the Western compatriots was not allowed under any circumstances, and Soviet science took a dark turn. Somehow, Ioffe and Kurchatov kept the atomic sciences out of the hands of the NKVD. Kurchatov kept his head down through the 1930s, publishing a few articles here and there when possible. Two scientists, Yuli Hiraton and Ikov Zedlovich, managed to repeat the experiments that Hahn and Strassman had done in 1938, and the potential for a nuclear chain reaction was realized in the Soviet Union. Beforehand, the idea of atomic power was only science fiction. When it was discovered, the potential for a weapon was not, and publication of nuclear physics continued until 1940. The last All-Union Conference on Nuclear Physics was held in 1940 as well, where Kurchatov discussed the idea of an artificial chain reaction. It's strange that two groups of scientists were working on the exact same problems on opposite sides of the world, basically independent of each other, save for the exchange of experimental results in the 20s and early 30s. But that was hardly, if any, collaboration. It seems our stories somehow always lead back to the Nazis, and this one in particular really does. All work on nuclear physics stopped on June 21, 1941, when the Nazis moved past the border and invaded the Soviet Union. The same date, Kurchatov and his team were going to start their cyclotron, which is a type of particle accelerator. He lost both of his parents in the war. By December, the fascists were at the door of Moscow, and a student in the Air Force, Grigory Fyodorov, brought to light the concept of an atomic bomb, and Ioffe listened. By 1942, Stalin himself was ready to begin development on an atomic bomb. The nuclear physicists created 3 labs. The one important to us is Laboratory 2, which would later be renamed the Kurchatov Institute for Atomic Energy. Kurchatov moved to Moscow in 1943 to head the uranium project. Just like their American counterparts, Soviet atomic energy was born through the atomic bomb. The lab was completed in 1944, and by that point the war was all but won, but development on the bomb continued without noticing it. It was only known by now that plutonium would be ideal for an atom bomb, and they also knew that it was produced through uranium fission. Anyway, I want to talk about the Soviet concept of the machine in the garden. This was the idea that nuclear energy was safe enough to be implemented next to a population center. They wanted to do this to show that technology was safe and under control. And now we get to the location chosen for the reactor, an abandoned field on the rim of Moscow, Oktoberfield. It was between 2 subway stations. Again, the parallels between the two groups is intense. They both used abandoned fields for God's sakes. Needless to say, their reactors were not parallel or even equals. The Soviet-designed F-1 reactor was smaller in weight than Chicago Pile 1, only 500 tons of graphite and 50 tons of uranium, and on December 25, 1946, almost 4 years to the date after Chicago Pile 1, the Russians reached criticality and operated the first nuclear reactor in Europe. Well, continental Europe, but we'll get to that later. The output was 4,000 kilowatts, which was mammoth compared to Chicago Pile 1's 200 watts. The reactor was also constructed quicker than Chicago Pile 1. Kurchatov is quoted as saying, "I remember the emotion which I and a group of my associates felt. For the first time on the European continent, we achieved a chain fission reaction in the Soviet Union with a uranium graphite reactor." And I'm guessing there were some mixed emotions realizing that that discovery would not be used for peaceful purposes. Some think the F-1 was designed through espionage, but there isn't much evidence backing that up, if any. And they also had the basic knowledge to build a reactor without outside help. I mean, I think I mentioned how close the scientists' experiments were, like, twice. Not to mention, the Soviets didn't have the luxury of not being invaded, unlike the United States. At any rate, it's not very important, because both reactors were built. Continuing with the story, the F-1 was proof in concept for the Soviets of plutonium production, and reactor development moved away from energy and into weapons development. The next reactor was designed by Nikolai Dyazlov. This was the infamous RBMK-type reactor. Side note, this guy lived to be 101. He designed these at the Institute of Chemical Machinery in Moscow with the support of Kurchatov's Institute. The first reactor of its type was constructed at Ozersk, but it was called Chernobylsky 40 at the time. Unlike the United States, who would find a place and kick people out of it, the USSR was different. Not only did they experience major population losses pretty much from the turn of the century, but Russia's population was much less than the United States. The Soviets would build entire cities around their nuclear program. They'd have shops, barbers, theaters, apartments, and everything your typical Soviet town had. The only difference was that they were closed off to the general population, only allowing nuclear scientists and workers onto the grounds. The area for production reactors was enormous, 200 kilometers squared. This was still tiny in comparison to the Hanford site. 200 kilometers squared is only about 50,000 acres. But that doesn't mean it wasn't important or producing. And produce it did. The first reactor on site, Reactor A, reached criticality on June 19, 1948. It operated with 1,149 vertical fuel vessels, typical of an RBMK design. All but 25 were loaded for the first reaction. It weighed a total of 1,050 tons, and it functioned at a maximum of 428 degrees Fahrenheit. It would eventually put out 900 megawatts. I couldn't find plutonium production stats for Hanford, but Reactor A produced 0.1 kilograms of plutonium a day at a ratio of about 0.1 kilograms of plutonium for every ton of uranium. The first plutonium harvest was on April 16, 1949. Eventually, another 4 reactors would be commissioned, and they ran up until the 1990s. F1, on the other hand, ran up until 2016. Holy shit. 70 whole years running an experimental pile. That's pretty impressive. Chernobylsky was eventually renamed Chernobylsky 65, experienced a radiation disaster in 1957, the Kalimsky disaster, which was the third worst nuclear disaster ever, but that's a story for another episode. For now, I want to talk about a country that we have never talked about on Come Hell or Heavy Water, France. France has 58 reactors running today, generating a staggering 71% of their total energy production, more than any other country. Why this reliance? France looks for something called energy stability. I don't want to go off track, but essentially, France doesn't want to rely on the volatile oil markets for their energy, and they have a, quote, respect for the environment. Whether you believe nuclear is good for the environment is up to you, and that's why I said that with an enunciation. Maybe I should do a nuclear pro-con episode. That might be too political, I don't know. Anyway, point being, France has got a history with nuclear power. France's nuclear program started off differently than both the United States and the USSR's. It started out strictly for peaceful reasons. Now I know what you're thinking. Wait, doesn't France have nuclear weapons? And yes, they do. We'll get to that. Either way, France's intentions at the beginning were peaceful. France was also looking toward the future, but not the environment's future. They saw atomic energy as being a huge moneymaker sometime down the line. In doing so, they thought, hey, why not build these things? We could make some cash. Unfortunately, they were wrong. The French Atomic Energy Commission was headed by a Dr. Korisky. He started planning for a Chicago Pile 2 style reactor, which was basically a safer version of Chicago Pile 1. They eventually wanted a reactor complex the size of Hanford. Where they would find suitable land for that, I'm not sure. Maybe they figured they'd build it off in the colonies somewhere. Who's to say? They began their research with a bigger than usual cyclotron. It was about 62 inches long, but France had some other serious limitations she had to overcome before they'd get anywhere near a reactor. They had to do everything by themselves: uranium enrichment, hydrogen furnaces, and chemical purification, just to name a few. Of course, all the states had to do this themselves, some under more stress than others, so USSR. But France was limited in their industrial, economic, and scientific capacity in comparison to the two superpowers. And they had just been bruised by the Second World War. Their nuclear development started only in 1948, and Korisky actually worked at the Los Alamos site. This does have some advantages as well, though. For one, they knew exactly where their money is going and how much is being spent, rather than their francs getting lost in red tape. They also had complete control over scheduling of shipping, so delays were essentially non-existent. Similar to the Soviets, the people working on the reactor were very young and enthusiastic. Probably for the same reasons, a new state just got out of 2 devastating wars, and the allure of a new and exciting industry. They were fresh out of universities, and the discoveries of fission were only a decade old. The potential behind the atom was limitless, and they were eager to learn and experiment, and that gave vigor to the French atomic industry. France also had some scientists working in the United States' atomic program, which gave them a solid base of knowledge that they could build off of in conjunction with the youthful enthusiasm that ran through the other scientists. With that all in mind, they were sort of isolated from other nuclear powers. NATO was a year away, and nuclear sharing was still a fever dream of anybody working in this industry. Furthermore, the United Kingdom and the United States weren't really keen on sharing their developments yet, and this was post-war, so the USSR wanted nothing to do with the West unless it was, well, war. Other states on the continent who would have some knowledge on nuclear physics were either barred from building reactors, like Denmark, or just completely ruined by war, like West Germany. France was essentially an island when it came to atomic development. Sure, they had some solid baseline knowledge on what was happening and how to do it, but they didn't have ready access to material and industry. A site was chosen, Fort Chatillon, which was quintessential in the Franco-Prussian War, but generally untouched in World War I and II. The site was just outside of Paris, giving easy access to scientists and politicians working inside of it. Construction began pretty much immediately post-war in 1946, with plans of starting up a reactor in 1948. Again, the plan was a Chicago Pile 2 style reactor to be built first, then move on to a Hanford graphite reactor, and eventually further progress from there. They started with the graphite, and they claimed, quote, "We are trying to do better, and at the same time we are developing physical testing methods similar to those used in your atomic laboratories. During the last year, using our own equipment and people just out of technical schools, we went as far as to measure the diffusion length of our commercially supplied graphite. From the start, we got the results as accurate or better than those we could obtain by chemical analytic methods," unquote. Essentially, that says, we're doing this on our own and we're doing it better. That sounds about right. The production of pure graphite, uranium, and heavy water was all underway and had never been studied before in France. They were pretty nervous about the chemistry side of things, believing that to be the bottleneck of atomic programs that started from scratch. Their expertise on that side of things was lacking, but they were also ready to push forward on the project. On the side of engineering, the French were set. They had electricians, mechanics, and engineers at the ready to build this reactor. The organization overseeing the project was the French Atomic Energy Commission. They were a civilian-controlled group and oversaw by the government rather than the military, something new in early atomic development. But this sadly changed. Some of the influential scientists on board were Professor Irene Joliot-Curie, Pierre Augier, and Francis Perrin, all of which were highly qualified for this type of work. The organization had tentacles reaching all across France. One of the most important was the La Bouchette chemical factory outside of Paris, which was responsible for uranium enrichment, but they ended up having to use natural uranium. Also, the Scalais site, which was used for a permanent nuclear research facility. In total, there were about 500 people working on the project, not including laborers. About 250 of them were at the Chatillon lab. With that, the stage was set for France to create its first experimental pile. Uranium was brought in from Morocco after an extensive 3-year search inside of France that turned up nothing. They secured a supply of heavy water from Norway, the same country which the Nazis got their heavy water from. On December 15, 1948, after 15 months of development, the experimental reactor ZO achieved criticality. Rather than producing power, it was used to provide radioactive isotopes for medical purposes and training future reactor operators. It took until 1953 for it to produce electricity, and even then it was only about 150 kilowatts. In fact, ZO stands for Zero Power Uranium Oxide Heavy Water, but, in French. And y'all have heard some of my attempts at Russian, and my attempts at French are much worse. The reactor wasn't necessarily built for electricity generation, as we went over, but for much different purposes. They did this because it took much less time to build if it didn't produce power. Zoa ran until 1976 and was shut down and decontaminated by 1977. It took France another 14 years of development before the first civilian plant came online at Chidon in the Lorraine Valley. Construction began in 1957. The reactor type would be a gas graphite reactor, which would produce plutonium. Yes, by now France had fallen victim to nuclear proliferation and began its weapons program. Electricity once again was a byproduct. The reactor was named EDF-1, and the construction and design of it forced it to be encased in a silver ball with a diameter of 55 meters. Pretty cool looking in my opinion. EDF-1 would have two sister reactors, EDF-2 and 3 respectively. Criticality of EDF-1 was reached September 16, 1962. Once again, weirdly close to my birthday. Electricity production began June 14, 1963, and after producing a total of 2.5 billion terawatt-hours of electricity, the reactor was officially completed on April 16, 1973. Today, the EDF-1 is partially dismantled and serves as a museum of atomic energy. EDF-2 and 3 were shut down in 1985 and 1990. And that's France's first nuclear reactors. We have one more country to talk about, another one to be featured on this podcast, and that is the United Kingdom. While the Soviet Union got to boast that they were the first to achieve an artificial nuclear reaction on the continent of Europe, the United Kingdom was the first to achieve it in Europe proper. Well, maybe, considering Brexit and all, they might not be a part of Europe, but that's very, very outside of this podcast, and I'll probably get flack for saying that. Anyway, in 1944, the British became interested in the potential of the atom. There was a joint British, French, and Canadian research facility in Montreal called the Chalk River Laboratories. They had been there due to, the war. They did build a reactor there too, and it was called, get this, ZEEP. What a cute name! And that was a trend for early British reactors, by the way. Arguably, because Canada was not yet independent, ZEEP was the first reactor on British soil, so we'll go over some stats for that. By the way, this was where the French got their baseline knowledge of reactors. Construction was approved on October 10, 1944. The reactor would be a natural uranium heavy water moderated reactor. In 1940 to 41, there was an attempt to make a powdered coke moderated CP1 style reactor, but this failed due to impurities in both the coke and uranium. That led to the decision of heavy water moderated reactors. It was cheaper, more available, and somewhat easier to build. The reactor was completed on September 4, 1945, and they reached criticality by the 5th at 3:45 p.m. ZEEP was the first reactor to operate outside of the United States. By the way, ZEEP stands for Zero Energy Experimental Pile. ZEEP served its purpose and gave the British, Canadians, and French baseline knowledge for nuclear reactors. It was upgraded and bugs were sorted out through its operating life, which lasted until July 27, 1970. With the success of ZEEP, the British took their papers home and began their quest for a truly domestic nuclear reactor. Sir John Cockcroft, who led the ZEEP project, saw the need for a domestic atomic program. So, in November of 1945, that's exactly what he did, and gained government support to establish, the Atomic Energy Research Establishment. A site needed to be chosen. Of course, it needed to be close to one of the major universities of Oxford or Cambridge. This was pretty much post-war, so the RAF was starting to wrap things up, and airfields were being sold off, abandoned, or reassigned for different projects. Raf Harwell, which was home to the number 38 group of the RAF, was chosen. The site was only 15 miles south of Oxford, allowing ready access to the top mines in the United Kingdom. It had ready access to workshops, roads, a water supply, and large hangars as well. The purpose for research was peaceful. They said, quote, 50% of the effort was in basic research, and 50% was to support some power production research. And, they were right. The weapons reactor would be developed at another site, Alderson, in 1950. But back to Harwell. The first pile reached criticality on August 15, 1947, with construction started little over a year before. It was a graphite-moderated reactor named GLEEP. GLEEP stood for Graphite Low Energy Experimental Pile, and it was low energy, producing only about 100 kilowatts. I feel like I should be referring to these reactors as he or she. I don't know what it is. Maybe they just sound really cute. Either way, GLEEP was an air-cooled reactor with 676 fuel channels. She was used to measure nuclei and create radioactive isotopes to be used in the medical field. something which is way out of my understanding. Another reactor was construction, and this one was named Beppo, which stood for British Experimental Pile. The O was added to harken back to the Marx Brothers. Yep, the British know how to name a reactor. Beppo reached criticality on June 3, 1948 at 3 p.m. He was a lot more complicated than Gleep and was able to produce 6 megawatts with only 250 fuel channels. Beppo was also used to produce medical isotopes, and these two reactors provided the majority of England's medical isotopes. Gleep operated until 1993, almost as long as F1, and Beppo was shut down only 2 decades later in 1968. Presently, the Harwell site is still used for atomic research. I think they're working on fusion right now, though it will be fully decommissioned and defunded by 2040. The next non-experimental reactor to be built in the United Kingdom was the reactor at Alderson. These reactors, as stated earlier, were not for peaceful purposes. Plutonium production from Gleep and Beppo wasn't efficient, so a new reactor was needed. Also, on August 1, 1946, the United States stopped its wartime sharing of knowledge with the United Kingdom, so if they wanted a bomb, they had to do it on their own. Britain set up an armament research establishment to begin, research of nuclear arms. It was headed by a Dr. William Penny, who worked at the Los Alamos test site. While there were many reactors to be built and experimented on at Alderson, the one we were focusing on wasn't built on site, just designed. The Windscale site was chosen and construction began in 47. And Windscale Pile 1 was completed in 1950, and Windscale Pile 2 in 1951. For the life of me, I cannot find the exact date they reached criticality. While Windscale was primarily going to be used for plutonium production, it was also the first civil nuclear reactor in the United Kingdom, kind of like EDF-1. Each core consisted of 2,204 tons of graphite blocks arranged in an octagon with 3,444 fuel channels in each. A total of 198 tons of uranium were needed to reach criticality. I may be wrong on this, but I believe they produced about 2,000 kilowatt hours each. The reactors had issues with uranium oxidization, and there was risk of the uranium catching on fire, which it did in 1957, but that's a story for a different time. After the fire, both reactors were shut down on October 10, 1957. Due to the fire, decommissioning will take up till 2040, and it has been ongoing since the 1980s. And that's how nuclear energy got its start, from a basement under a field in Chicago to generating 14% of the world's energy. I'm also going to stress that all of these reactors led to nuclear proliferation, which in my opinion is very sad. While yes, some scientists wanted to take this route, others like Hahn and Miter, for example, abhorred the idea, and I guarantee you that they were not alone. Also, I'm sure some of y'all are wondering why I didn't cover the Germans' Urian project and the Japanese Nigo project, and that's because I'm saving them for another episode, and, well, they never reached criticality, or in the case of Japan, never even got close. Thank you all for listening. This has been Nathan Coggeshall with Come Hell or Heavy Water. Hope to see y'all in the next one.